Okay, are you able to share the screen?
I thought I was sharing, sorry. I will try again.
No problem.
Now?
Yes, so our second speaker is Silvia from TUM Munich, Germany, and she's going to talk about the Schwinger effect, vacuum instability, mode mixing, and quantum signatures. Maybe I send you a reminder when 5 minutes are left.
Thank you. Thanks everyone for coming and thanks for inviting me. So yes, I'm Silvia. I'm a postdoc at the Technical University of Munich, and today I'm going to talk about different aspects of the Schwinger effect. So I will try to keep it brief because we only have half an hour and I want to share several things. So this is the overview slide, sorry. And what I want to do here in this slide is to make sure that we are all in the same page and that you understand what I mean when I talk about the Schwinger effect. So let's start by defining the Schwinger effect. So it is usually defined, or for me, it will be the spontaneous creation of particle pairs out of the vacuum when a very strong electric field is present. So classically, this is an effect that wouldn't happen. So if we have a very strong electric field, we expect it to be stable. But quantum effects, when we go to the quantum theory, we know that there is a certain probability that this very strong field decays, creating pairs of particles out of nothing. So the goal of the talk would be not only to understand the Schwinger effect, I will give some hints or some ideas about how to compute the Schwinger effect, but the goal would be to understand the Schwinger effect from a more quantum information perspective. And in particular, I will try to talk about quantum aspects of the Schwinger effect, entanglement in the Schwinger effect. And then if time allows, I would also like to mention a bit how the Schwinger effect is related to other effects in nature that are very interesting, like gravitational particle creation, Hawking effect, because after the talk, I hope you are convinced that those things are all very related, or they are almost the same. So I will try to answer some questions in this talk, and the questions are as follows. So first, I will try to explain you how the Schwinger effect can be derived. So in general, there are several methods in the literature to describe the Schwinger effect, and I will focus in one. The one that I will choose is the one related to the so-called Bogoliubov transformations, and I would choose this method because it's the right method to then ask questions about quantum information. Then we would go to the main part of the talk, that would be to ask under which conditions these particles that are created via the Schwinger effect are entangled. So when are those entangled, and how this depends on the external parameters, like for example, on the temperature of the environment. And then point number 3, if time allows, again, I would make some comments about differences between bosonic particles and fermions, and about how all this is connected to gravity, which I think is quite interesting. So let's start from the beginning. Part 1, the Schwinger effect. Okay, so again, let me remind you again, what do I mean when I say the Schwinger effect? This is the spontaneous creation of particles out of the vacuum, out from nowhere, in the presence of a very strong electric field. And as I said before, also, it shares deep connections with cosmological particle creation or with the Hawking effect. However, it was formulated in a context or in a mathematical framework, which is very different from the mathematical framework used for the Hawking effect. It was described in the context of quantum electrodynamics and in the context of effective actions, imaginary part of the effective action. So if you tell me that I should summarize the Schwinger effect in one formula, I would choose formula 1. This is a decay rate. This is related per unit time and volume, and is related to the probability of the vacuum decaying and creating these pairs of particles. We have here a prefactor that depends on the dimension of the space-time, and then we have here this exponential part, which is the main part of this formula, I would say. Let's focus on n equal 1 because it's the dominant effect. And then we see that this decay rate is exponentially suppressed unless the electric field is strong enough. So this exponent actually sets a natural scale at this electric field and these natural units. Here I put H bar and C. This sets a scale up starting from which the Schwinger effect would be relevant and could be detected. So if electric field is very low, this is irrelevant in our physics. And then if electric field is high enough, then we can expect to observe this effect in potential in the lab. But the next natural question would be if this effect has been actually measured, detected. So this slide is not very deep, but I wanted to give you some context. So regarding the real Schwinger effect, the one predicted from vacuum QED, if one does the computation for this critical field, one realizes that this critical field is very strong, and it requires very high intensities in laser facilities to produce this strong electric field. We are not able, as a humankind, to produce these high intensities in the lab. So then particle creation related to the Schwinger effect and vacuum QED has not been detected yet, although there are some subtleties and some enhancement techniques that can be used to lower maybe this threshold, but for now it hasn't been measured. More interesting, maybe, more interesting in the sense that it can be measured now, is the mesoscopic Schwinger effect. That is this analog Schwinger effect, but instead of in vacuum QED, it would be in graphene. So instead of having electron positrons, we would have electron holes, and instead of being in 3D, we would be in 2D. But the same formulas and the same computational techniques can be used to describe mathematically this effect by making the right replacements. And for example, for this mass gap, which is a characteristic of the material, then the critical electric field to produce this effect is accessible. And actually in 2022, it was reported an experimental result in graphene that it's compatible with the Schwinger effect. So I think this is a promising platform to make predictions or to try to understand Schwinger effect from a maybe broader or deeper perspective. So I think it's nice that we have access to this effect experimentally, even if for now it's from analog platforms. Okay, let me now stop talking about experiment and let me focus on the more technical part of the talk. So in these following slides, what I'm going to do is to try to describe how to obtain the Schwinger effect, how it's possible that particles are created out of the vacuum from this Bogoliubov transformation method. Again, sometimes people describe or are able to obtain a Schwinger effect from these effective action techniques, this imaginary part of the effective action, but I'm going to focus in this alternative derivation that is based on time evolution and real-time evolution, and it's based on understanding that the vacuum that we have at initial times doesn't coincide with the vacuum that we have at late times, because there is some time evolution of the background, and this fact is the one that is making particles to be created out of the vacuum. So I will now, in this slide and the next slide, try to tell you how this works, but I wouldn't show equations, I would be mostly talking, so I hope it's fine. So for simplicity, let's think about scalar fields, and let's consider a free scalar field with mass m and charge e, propagating in a classical homogeneous, this is very important, electric background that can be parameterized, as you can see here. So then the idea would be to try to study the evolution of this field and then see if particles have been created or not. So since we have this homogeneity, we can do a Fourier expansion of the field and then work instead of with the field modes. And then when we study the equation of motion for this field mode, we realize that it's a second order differential equation, and then it can be solved in terms of a basis of solutions that has like two linear independent solutions. And we realize that there are two natural bases to express this solution in terms of. So this is the basis called the in basis, which is the set of solutions such that at early times, when I expand the solution for t going to minus infinity, they look like positive frequency solutions, like plane waves. And there is another basis, which is the basis of solutions, or those are the solutions such that when I take them and I expand them for t going to infinity, they look like positive frequency solutions. Then what is interesting here is that even if I didn't say it explicitly, these two bases do not coincide because there is a time dependence of the background that in this case is parameterized via the vector potential. So the vector potential for this electric field looks like that. And then this causes that the solutions are not plane waves, although asymptotically they are, and that these two bases of solutions do not coincide. They are not the same. However, since they are solutions of a given differential equation, which is unique, they have to be related via a linear transformation, okay? So then this linear relationship between these bases of solutions that are good for having plane waves at early and late times translate into linear relations for the creation and annihilation operators. So this means that we would have, given that we have two different bases of solutions, we would have two different sets of annihilation creation annihilation operators that describe my vacuum state and my particle states. Those are not the same, but are related linearly, but the so-called Bogoliubov transformation that you can see in two. Those are the Bogoliubov coefficients. And these relationships, let me tell you that they are very simple because the background is homogeneous. So then this mode mixing is only happens for pairs of modes with momentum k and minus k. So this is Bogoliubov transformation that is relating my ladder operators at early and late times and is relating my early time vacuum with my late time vacuum. Those are important because those coefficients are the ones that are encoding particle creation, vacuum decay, and so on. In particular, for the case of a constant electric field, they look, I would say, simple. And then this computation can be extended to other background fields, like, for example, electric poles and so on. Now, from this transformation, we can then compute all the observables related to particle creation at late times. For example, we can compute the number of created particles at late times. And then this is proportional to these beta coefficients. And then we can also do some computations that are more related to this effective action formalism. For example, we can compute the vacuum persistence amplitude, which is the probability that the vacuum remains the vacuum. And then we realize that it's not one. So there is some probability of decay. And actually we can, I'm not showing here the computation, but we can relate the result we obtain with this decay probability that I showed you in the first slide. Okay, so far so good. This is just an introduction. This is just to let you know how particle creation happens in the Bogoliubov formalism. And now we are going to go a step further and discuss about quantum information or entangled, because the idea would be not only to show, as I did here, that particles are created, but the question to answer would be if these particles are entangled and under which conditions. So what I'm going to do now is to first define entanglement and then show the function or the quantifier that I'm going to use to state that a pair of modes or of particles is entangled or not. And then the computation would proceed as follows. We would choose an initial state that can be the vacuum or can be a thermal state that is described by an initial density matrix. And then we would let the system evolve and we would see how this state looks like for the out observer, because we are in the Heisenberg picture, so states do not evolve, but then our field evolves, ladder operators evolve, and then this is what I mean when I say it looks like for the out observer. And then I will show you particle number, entanglement for different cases, and then we will discuss how everything depends on the external parameters. And then we will focus on bosons because they are easier to understand. Okay, let's start. What do I mean by entanglement? So let's consider a quantum state described by a density matrix that is acting on some Hilbert space that admits a partition. This is very important. This, like for example, this partition that you see here. Then we say that the state is separable if it can be written as this decomposition that you see in 7, where rho A and rho B are density matrices that act only on HA or HB. If the state cannot be written like that, then we say it's entangled, okay? So the key feature here is that to determine if something is entangled or not, we have to determine a bipartition of the Hilbert space. This is what would tell us if this initial state, this state, or these modes, particle modes, are entangled or not. Now, this is an abstract concept. It could sound complicated, but it simplifies for the Schwinger effect. First, because the Schwinger reproduction, because of the homogeneity of the background, happens in pairs. So we don't have to study the full density matrix of the system, but we can focus in the reduced density matrix for a given pair of modes, particle and particle. And then again, to discuss entanglement, we have to specify a bipartition of the Hilbert space. And in this case, the most natural bipartition is the out bipartition, and because this is the one related to our definition of particle states at late times. So the question that we would try to answer is if the reduced, with reduced I mean for a given set of pair of modes, if the reduced density matrix is separable or entangled with respect to the out bipartition. This is the question that I would try to answer, and that would let me know if these particles, Schwinger particles, are or not entangled. Okay, this slide, I decided to reduce it a lot because before I had a lot of definitions, but basically what I said is still too abstract. We want to have a function or a quantity that we compute it, and it gives us a number, and then from this number we infer if these pairs of particles are entangled or not. So we decided to work with the logarithmic negativity, which is a quantity that is built from this density matrix. I'm not showing you how, but it's built from this. It's good because it works for mixed states, like thermal states. And it's also good because for Gaussian states, like if we choose some initial Gaussian state, the computation of this quantity simplifies. And then it would give us this computation would be simple, and then we would have something that depends on the Bogoliubov coefficients and on other external parameters like the temperature. And the property of the logarithmic negativity is as follows. If it gives 0, there is no entanglement. I should not use detected, there is no entanglement. And then if there is bigger than 0, there is entanglement. So I'm not showing you how to compute the logarithmic negativity, but I'm telling you that I can use this quantity called logarithmic negativity. Given an initial matrix, I can compute it, and then it would, depending on the value, I would be able to say if there is or not entanglement. Okay. So let's go to the results. Let's go let's focus on bosons because everything is simpler to understand, and let's say the formalism is better developed for bosons, and then we will comment on Ferments later if we have time, that I think we do. Okay. So again, I'm repeating a lot. The question to answer is if Schwinger pairs are entangled. And then we have to choose some initial state, let the system evolve, and see what happens at late times. We focus on vacuum state or on initial thermal states, and then we compute systematically particle number and logarithmic negativity. And then I'm advancing you, or I'm telling you the final result, so you are prepared for the next slides. So for the vacuum state, entanglement is always present. We would see that logarithmic negativity is always in 0. But for thermal states, entanglement can be destroyed, and can be destroyed if the temperature is too high, because temperature destroys the entanglement, or if electric field is too low. If electric field is too low, entanglement would be lost as well. So let's see how it's more quantitatively. So let's start with particle number. We start from an initial thermal state. Bosons at temperature T initially are described by Bose-Einstein statistics. So then we have this particle number at early times and with this distribution. Using this Bogoliubov formalism method, we can from the in state obtain the results for the out state in terms of the initial condition and then the Bogoliubov coefficient. And in particular, we can do the computation and we obtain something that looks like 11. So we have that the particle number at late times depend on this Bogoliubov coefficient, which at the same time depends on the electric field. And then we also have this thermal factor, which is a thermal enhancer, which means that for bosons, if we have temperature, we produce more particles because of this thermal enhancement, which is a property that we do not have for fermions. It is a very interesting fact. Okay, so now let's go to the logarithmic negativity. We can compute and analyze the logarithmic negativity that can be obtained in terms of the Bogoliubov coefficient beta and the temperature. And we observe as what follows. The higher the beta is, the more entangled is the system, which means the higher is the logarithmic negativity. And then the higher is the temperature, we see the opposite. The lower is the entanglement. And actually, if the temperature is too low, entanglement is completely destroyed. So temperature, if the temperature is too high, entanglement is completely destroyed, which means that the temperature should be lower than a given threshold to have particle creation. And what is more interesting is that even if this beta is related to the electric field, beta going to 1 implies electric field going to infinity. And even if my electric field goes to infinity, there is a critical temperature above which entanglement is destroyed. So it doesn't matter how strong is my electric field. If temperature is too high, entanglement will be destroyed. So let's see in a plot what I said in words. So here I'm plotting the logarithmic negativity in terms of temperature and beta coefficient. So we see what I said in words. So if we fix beta, we see that as we increase the temperature, logarithmic negativity decreases at some point is 0. And if we fix temperature and we increase beta, which means that we increase the electric field, the logarithmic negativity increases when it's higher than this threshold. Okay, so I said everything in terms of beta, but it's more natural to talk about electric field. So what I said translates in this fact that you see in 14, that only when the electric field is bigger than a threshold for a fixed temperature, we would have entanglement. Otherwise, it would be destroyed. And one interesting thing that we have for bosons is that we have two critical fields. We have the electric field to have entanglement, this critical field to have entanglement, and then we also have a critical electric field to have particle creation, which is related to the electric field that I told you in the first slide, that relevant particle creation only happens if the electric field is bigger than some quantity that is critical. So it's interesting to see how these two electric fields compete. And okay, the results are as follows. If the temperature is low, the critical electric field for entanglement is lower than the critical electric field to have particle creation, which means that pairs of particles would be entangled, but on average, we would not produce particles enough, so this wouldn't be detected. And as we increase temperature, then this critical electric field to have entanglement blows up. So then we would have maybe more particles that are created, but they won't be entangled. So it's easier to see it in a plot. So in the black line, I'm showing you the critical electric field to have particle creation. And here is the critical, in blue, is the critical electric field to have entanglement. So we see that at zero temperature, any field creates entanglement, but only if the particles will be produced in a significant amount of, significantly, if the electric field is higher than this critical electric field for particle production. As we increase the temperature, the critical electric field to have particle creation decreases, which is it's easier to create particles because of this thermal enhancement. However, the critical electric field for entanglement increases, which means that it's higher to detect entangled pairs. Okay, so this is interesting because creating more particles doesn't mean that these particles are more entangled. And then if this temperature is too high, we would create, yes, more particles, but they won't be entangled at all because there is this temperature threshold. Okay, so then I had time, I was quick. So in the last part, I'm going to discuss about fermions, and I'm going to discuss about connection to gravity. What I did before was all for bosons for many reasons. First is because conceptually it's easier to understand, and then because the literature focused mostly on bosons for other reasons, because a lot of the techniques that we are using here are borrowed from quantum optics, and there I guess it's more natural to talk about bosons. So now I'm going to tell you very briefly how the picture changes if we discuss about fermions. So first, it's important to notice that the Bogoliubov formalism can be applied also for Dirac fields. We can do a mode expansion and study the ladder operators, but some things change. The Bogoliubov matrix that we had before, now for fermions, has a different shape. In particular, has here a minus sign, and also the normalization condition changes. And this would affect to the statistics and the particle number at late times. Then for Gaussian states, we can also use something called the Gaussian formalism that I didn't actually introduce for bosons, but it's important for the computations, but it has to be adapted to the structure of fermions. And then the third part, and the more interesting part, is that the entanglement can be also computed using the logarithmic negativity, which actually is based in something called PPT that I didn't explain to you. However, it has to be adapted. We cannot use just blindly the formulas that we have for bosons. We have to adapt them for fermions. At least this was done and was proved to be correct not many years ago. So it's a field that is still developing, and I think it's quite interesting. But okay, one can take the formulas adapted for fermions and do similar computations because the broad picture applies. Okay, so let's see briefly the results, particle number for fermions. For fermions, we also focus on initial thermal states that are described by these statistics, and we can also compute temperature and logarithmic negativity. We can compute particle creation and logarithmic negativity. If we compute the particle number at late times, we see again that it depends on the Bogoliubov coefficient and on this thermal coefficient, which in this case is not an enhancement, it's a suppression coefficient, which means that the more is the temperature, the less particles will be created. If we compute now the logarithmic negativity for fermions, we realize that the pattern or the behavior is very different compared to that for the bosons. We see that, okay, again, as when we have fixed electric field or fixed beta, as temperature increases, the logarithmic negativity decreases, which is similar to bosons. But what happens is that it never goes to zero. It's a smooth function, which means that entanglement is naturally more present for fermions and for bosons, because even if logarithmic negativity goes asymptotically close to zero, it's never zero, okay? And then at fixed temperature, we see that the logarithmic negativity has a maximum, not at beta square equal 1, as it happened for bosons, but at beta equal to 1/2. If we translate this condition, 1/2, to the condition for the electric field, we realize that what this means is that there is a maximum electric field for entanglement. So what means is that if the electric field is bigger or smaller than this one, then entanglement will be lower. And this is quite interesting, and we do not have an analog for bosons, because for bosons, as we increase the electric field, entanglement increases. So this is a property which I find very interesting, and is not, again, present for bosons. Here I show you a plot about the logarithmic negativity for fermions, and it shows what I said before. We see that there is always color, which means the logarithmic negativity is never zero. We see that at fixed beta, as we increase the temperature, logarithmic negativity decreases. And then at fixed temperature, we see that as we increase the electric field, or beta, we first increase logarithmic negativity, we reach a maximum, and then we decay again, which is quite interesting because it's a behavior for only present for fermions. Okay. So, now I'm going to talk about gravity. I will spend only a couple of minutes because we don't have more time. So I want to tell you how all this story is related to Hawking effect and to particle creation in cosmology. First, I want to let you know that to study particle creation in cosmology and in black holes, the original formalism that was proposed was this Bogoliubov transformation formalism. So the same techniques can be applied. The techniques that I told you for the electric field can be applied for cosmology. In particular, in cosmology, since the background is homogeneous, particles are also produced in pairs. And since background is time-dependent, the in and out bases do not coincide, and this is what creates in this formalism particle creation. In particular, the ladder operators can be related via this Bogoliubov transformation, which is the same as before, but now instead of writing it in terms of alpha and beta, I took the freedom in reparameterizing alpha and beta in terms of this R and this angle. Why? Because this is something that it's a transformation which is called a two-mode squeezer that is used in quantum optics that has some nice properties that had been studied. And then in this language, we are able to understand particle creation in both the Schwinger effect and in cosmology as a two-mode squeezing process in quantum optics. We could even draw a quantum circuit if you want, a symplectic circuit that is called, which would look like that. So this is the quantum operation that we do, in, out, and then we say, okay, so particle creation both in cosmology and in the Schwinger effect is just a two-mode squeezer in this language. So it's maybe for those who are more familiar with quantum optics, it's simpler to understand. Now, what happens with Hawking radiation? The same formalism, the Bogoliubov formalism, can be also applied for the Hawking effect. Actually, this is how Hawking obtained particle creation or Hawking radiation. However, the problem here is more subtle because here the Bogoliubov transformations are not trivial because we do not have naturally this mode splitting because the background is not homogeneous. So we would have something more complex like in 21. However, it was shown for other reasons many years ago that we can do a smart change of basis such that this mode mixing happens in groups of 3. So in 3 mode blocks instead of 2. And what we have are 2 different processes in this quantum optic language. First, we have a two-mode squeezer, which is the one related to particle creation. And it's related, it produces entanglement as before. And it is, let's say, is related to parameters of the black hole or of the horizon. And then we have a beam splitter, which is the second process or the second thing that happens that is related to this scattering. Okay. And that this preserves particle number. This doesn't create entanglement, but this is part of the Hawking process. So basically, particles are created, but then since there is this potential barrier, one mode reaches us and the other falls into the horizon. So one can say that, okay, particles are created, one mode falls into the horizon, the second tries to reach us, and then as this mode propagates to us, then there is some kind of backscattering, if you want, and only part of it reaches us. So this is related to transmission and reflection. So if we want to express it again, sorry, here I'm not being very detailed, I'm just giving concepts or ideas, and then if you want to see the deep analysis of what I'm saying, you should go to this paper, which is quite nice and discusses very interesting space-times, not only one black hole. Okay, so then if we want to do this quantum circuit, or if we want to express this physics of the Hawking effect in a quantum circuit, I'm telling you, I'm not proving, of course, that it can be decomposed into operations, which are TUM squeezer, that is the one that produces entanglement and creates particles, and then this beam splitter, which is related to this scattering or to this potential barrier. Okay, so I don't have more time to say things about this aspect, but okay, I think the core of this last part was to convince you that the Schwinger effect, Hawking effect, and cosmological particle creation are not that different. They can be studied using the same language, and more than that, if we are interested in, for example, analog gravity, we can even simulate weirder space-times. Like, for example, I know in some experiments they simulate a black hole and a white hole and things like that. And all these experiments can be modeled using this language, which is partially which is explained in this paper, which I think, again, is very interesting. So that's it. That's the end of my talk. So yes, a brief summary of what I said and why I think it's important. So first, here, this I didn't explicitly say, but basically the Schwinger effect can be obtained in different frameworks, can be obtained in effective actions, also using the word-line formalism and using Bogolubov. Those techniques are different, but they are related because they give the same prediction at the end of the day. We decided to use this Bogolubov transformation method because it's a mode-by-mode method, and then it allows us to compute entanglement and to compute to answer the interesting questions. Then regarding entanglement, we see that it's not automatic, although it tends to be present. For bosons, if temperature is too high or electric field is too low, there is no entanglement. For the vacuum, there is always entanglement. And then for fermions, entanglement is always present, although is strongly suppressed with temperature, which means that we may not be able to detect it even if it's there. And then the last part of the talk, it's about cosmology, black holes, and Schwinger effect. So I try to convince you again, only with my comments, not with any technical computation, that the same physics or the same, techniques can be applied to obtain particle creation in cosmology, Hawking process, Schwinger effect, and they can all be described in terms of these symplectic operations that we have. This is for bosons, okay? The word symplectic. And I think that's it. I think I can stop now. And thanks for your attention. I'm happy to answer questions. And again, since the time is very limited, otherwise you can write me an email.